Welcome to Mrs. Z's Chemistry. In this chapter, we are going to learn how to solve some equilibrium problems. So far, the equilibrium problems we've seen give us the concentrations at equilibrium so that we can solve for the equilibrium constant, or the K. In order to solve for the equilibrium constant, K, we must have values at equilibrium. Well, some problems will only give us a value initially, before the system has reached equilibrium. And then we need to solve for what the equilibrium values are before we can plug in those values into the K expression. The initial amount is just the beginning amount. The word species in this context can mean any atom, ion, molecule, compound, or any particle in any state of matter: gaseous, liquid, solid, aqueous. Stoichiometry, again, just means the relationship between moles, ratios, or the coefficients in a balanced chemical reaction. So if we have this example, equilibrium reaction of NH3 turning into nitrogen and hydrogen, and if we start out with only some NH3, we don't know how much is going to turn into the products. And we know that not all of it gets to turn into products because this is an equilibrium reaction, not a completion reaction. So if at equilibrium we found that there was some value x of nitrogen, that means we know that nitrogen changed by a value of x. And then hydrogen, we can expect, would have changed by 3 times x, because there's a coefficient of a 3 on hydrogen, whereas there's only a coefficient of a 1 on the nitrogen. N2 and H2 are products, so we are adding that some value of x and adding the some value of 3 times x. And then NH3 will have changed by a value of 2x. It's going to decrease from the initial amount by 2x. So let's start with an example. Suppose we start out with 16 molecules of NH3 and 0 of each product. We're going to use a Rice table or ICE table: reaction, initial, change, and equilibrium. The initial value is the initial value we have of each. In this example, we have 16 NH3, 0 of each of the products. Then we allow the system to reach equilibrium, and the change row is filled in with values of x. The number in front, the 2, or the invisible or implied 1, or the 3, come from the coefficients, 2, 1, and 3. So that means NH3 will change by a value of 2x, and we're going to subtract that amount from our initial. We're going to add a value of x to the nitrogen and add a value of 3 times x to the hydrogen. The equilibrium row is found by taking initial and adding it to the change. So we're going to take 16 and then add a minus 2x to get 16 minus 2x. We're going to take initial of 0, add the change value, and we get x, because 0 plus x is x. 0 plus 3x is 3x. So then we could use the K expression or some other information to finish the problem. Let's go ahead and look at a different example. Carbonyl dichloride, COCl2, decomposes according to the following reaction. Initially, 0.06 molarity of carbonyl dichloride only was placed in a sealed container at a certain temperature. So let's start right here. Notice the word only. That means we only have this compound in the system, and we have 0 of each product. We could find the change row as minus x, plus x, and plus x. Each of the coefficients are 1s, so we don't use coefficients here. The reactants on the left side of the reaction of the arrow is always negative or subtracting because they're being used up, and then the products are always positive or adding. Then we take initial and add it to the change, so 0.06 minus x, and 0 plus x is x, 0 plus x is x. So now let's notice the second sentence the third sentence of the problem here. At equilibrium, there was this value of carbon monoxide in the container. So that means this whole box can be replaced with 4.6 times 10 to the negative 5. That value is what x is equal to, because if 0 plus x equals 4.6 times 10 to the negative 15, or -5, we can see that that is what X is equal to. And therefore, we have that same value over here for the chlorine. So both chlorine and carbon monoxide have the same equilibrium value of 4.6 times 10 to the -5. You cannot get a carbon monoxide molecule without also getting a chloride molecule where the only place they're coming from is carbonyl dichloride. So then we can plug in this 4.6 times 10 to the -5 value for X into our equilibrium value. Pause and type that into your calculator, 0.06 minus this value. You should get 0.05995. So these are the equilibrium values. Now we can plug in these values into our K expression, which is this, products over the reactants. So we have our products multiplied together. Our products can be plugged in as 4.6 times 10 to the -15. Here's the products in the numerator. Then the denominator is the COCl2, which is right here. Pause and type this into your calculator, and you should get 3.5 times 10 to the -8. Let's try another example. Nitrogen oxides are air pollutants produced by the reaction of nitrogen and oxygen at high temperatures. At 2000 degrees Celsius, the value of the K for the reaction is 4.1 times 10 to the -4. Calculate the equilibrium concentration of NO if the equilibrium concentration of nitrogen is this and oxygen is this. The only reason why we would use a Rice table is if we were only given initial values. But in this problem, we're given equilibrium values, so we can just go straight to our K expression for this reaction and plug in the values we know and solve for the one that we are asked for. This is the K expression. The product is NO. It goes in the numerator. The coefficient of the two turns into the exponent. The reactants are N2 and O2, but there are no coefficients other than a 1, so they go in the denominator. Remember that these are multiplied in the K expression. We have this value for nitrogen, that goes here. We have this value for oxygen, that goes here. We also have the K value as 4.1 times 10 to the -4, and that goes here. Plug in all of your values, and you should get this. If you multiply your denominator on both sides of the reaction, or both sides of this equation, we get this so far. Then we have 1.31 times 10 to the -7 is equal to NO squared. But the problem is not asking for NO squared. It's asking for the value of NO. Therefore, take the square root of it, and we have our answer. Let's try a third example. Under certain conditions, the equilibrium constant K for the decomposition of PCl5 into PCl3 and Cl2 is 2.1 times 10 to the -7. What are the equilibrium concentrations of PCl5, PCl3, and Cl2 in a mixture that initially contained only 1 molarity PCl5? Those words that I just underlined, those are the key words you're looking for to know whether or not you need to use a Rice table. Initially, we only have this value of PCl5. In order to solve for the equilibrium values, that's this row of the Rice table, that last E row. We have 1 initially of PCl5. We have 0 of the products because it said only. The mixture initially contains only this reactant, PCl5. Pause and see if you can fill in the change row and the equilibrium row. The change row is in terms of X. PCl5 is going to decrease or subtract by a value of X. PCl3 are going to increase by values of X. Because all of these have coefficients of 1, they're all going to change by the same value or same amount. And now we have 1 minus X for the equilibrium. This is 1 minus X equals 1 minus X. 0 plus X equals X. 0 plus X equals X. If we plug this into our K expression where we have products over reactants, here's the product for PCl3, and then the product for Cl2 goes here. The numerator is 1 minus X, that is here. This value, the 2.1 times 10 to the -7, that is the K. Now, if you're looking at this problem and you realize you need to try to solve for x, this is going to be difficult. You're going to need to use the quadratic formula for this. But even on the AP Chem exam, the quadratic formula is not needed. And the reason is because whenever this shows up in these types of problems, the change, or the x, in concentration is so small that the initial value of 1 is still 1, the same initial concentration, when rounded to correct significant figures. 1 minus x is still 1 when you round to 2 sig figs. So you can ignore the x in the denominator. We're going to talk more specifically about this in a moment, but let's look at how the math changes. If we just take out the x from our denominator, we now have this. 1 minus x is still 1. So let's not complicate the math by trying to put a minus x in the denominator. Now you can see this requires just simple algebra to solve. Multiply 1 on both sides of the equation, and that gives us this. 2.1 times 10 to the negative 7 equals x squared. Take the square root of that value, and you get this. So this is your x value. The original problem asked us to solve for the equilibrium concentrations of each. So we're going to plug in this value of x here, here, and here. So we can see that the two products, PCl3 and Cl2, are equal to each other because they're both equal to x, which is that value. Let's take PCl5. 1 minus x is 0.99954, while appropriate significant figures is 1.0. So here's specifically how we are able to ignore that x in the math, which kind of feels like we're cheating or fudging math in some way. You can assume that x is small enough to ignore in the denominator when the k value is smaller than 1 times 10 to the negative 4, so that means 1 times 10 to the negative 5 or negative 6, something like that. Or if you're not given the k, if you're given the x value, if the x is much less than the initial concentration, that when you try to take the initial concentration minus x, you still get the initial concentration when you round to appropriate significant figures, that is when you know you can ignore the x in the denominator. The whole reason for this is to avoid having to use the quadratic formula. If you have the quadratic formula program into your calculator, go ahead and type in all the values using that x in the denominator, and you'll see that even though you do all this more complicated math, you're still going to get the same value for x than if you just ignore the x in the denominator. This is really important though. No matter how small x is, you never can ignore it in the numerator.